Good morning everyone, especially to our professor, Sir Ellvan Campos. As part of our requirements for the subject STM 604 or Differential Calculus, I, Brian R. Añober, together with Miss Queenie C. Damalerio, will present to you this video explainer about mixture problems. Mixtures is the mixing of two salt solutions of differing concentrations gives rise to a first-order differential equation for the amount of salt contained in the mixture. The general equation involved in solving this kind of problem is dq over dt equals the input rate of salt minus the output rate of the salt, or in symbols, R sub in minus R sub out, where R sub in is equal to the concentration of salt in inflow times the input rate of the brine. So that will be the input rate of the salt. On the other hand, R sub out is equal to the concentration of salt in outflow times the output rate of brine, and that will be the output rate of the salt. Now, let's have this first example. A tank contains 1,000 kg of salt suspended in 10,000 liters of water. A mixture of 2 kg of salt per 10 liters of water enters the tank at one end at a rate of 4 liters per minute. It is mixed with what's in the tank at the other end. The mix leaves the tank at 4 liters per minute. Now, we are tasked to find Q of T, or the amount of salt in the tank after T minutes. Then, we will also find the limiting amount of salt in the tank. Since the amount of salt changes continuously over time, we need to look at the rate dq over dt. We will use the general equation dq over dt equals rate in minus rate out. We will use the general equation dq over dt equals rate in minus rate out. Then, substitute for the values of rate in and rate out. Observe how the units will simplify to kilogram per minute on both cases. For rate in, we have 2 kg per 10 liters of concentration for the inflow times the inflow rate of 4 liters per 1 minute. Then, subtract the rate out, in which the output rate is also 4 liters per 1 minute, then multiply to the concentration of the outflow, which is Q of T kilograms, since the amount of salt after time T is still unknown, over 10,000 liters, since the tank can hold 10,000 liters of water. So, our equation will look like this. By doing the algebra and simplifying this equation, we will now have this equation. dq over dt is equal to 4/5 minus 0.0004 q of t. Now, let's consider this simplified equation earlier. We have q prime, or dq over dt, which is equal to 4/5 minus 0.0004 q, and remember that q of 0 is equal to 1,000, since there is an initial amount of 1,000 kilograms of salt in the tank. Now, let's rewrite this equation as q prime plus 0.0004 q equals 4 over 5. We will then use the integrating factor to find the value of our q here. So the integrating factor will be mu of t equals e raised to the integral of p dt, or for this case, our p is equal to 0.0004, since it is the coefficient of our q above. So we have here integral of 0.0004 dt. So simplifying this, will come up with e raised to the power of 0.0004 t. Thus, our q of t will then be equal to the integral of 4/5, or the constant here from our equation earlier, times the integrating factor of e raised to 0.00040 times dt plus c all over the integrating factor e raised to 0.0004t. This will then become 4/5 times 1 over 0.0004 from our integral earlier times e raised to 0.0004t plus c all over a raised to 0.0004t. By simplifying, we'll come up with 2000 e raised to 0.0004t plus c all over e raised to 0.0004t. Previous equation will then be simplified as q of t equals 2000 plus c e raised to negative 0.0004t. Then, using the initial condition, which is q of 0 equals 1000, we will solve for the value of c. The equation will become 1000 equals 2000 plus c times 1. So the value of c is negative 1000. Thus, the particular solution is q of t equals 2000 minus 1000 e raised to negative 0.004. As t approaches infinity, the term e raised to negative 0.0004t approaches 0. So the limiting value of salt in the tank is 2000 kg. This should make sense. In a 10,000 liter tank with a mixture that is 1/5 salt per liter coming in for an extended period of time, we should expect that 1/5 of the total volume or 1/5 of 10,000 is equal to 2,000 kilograms, which is salt. And so our problem is solved.
So we have here another example. Our example number 2. A vat has a capacity of 15,000 liters. It initially contains 2,000 liters of water in which 50 kilograms of sugar has been dissolved. A mixture of 1.5 kilograms of sugar per liter of water comes into the vat at 5 liters per minute. It mixes with what's in the vat, and at the other end, the mixture exists at the rate of 3 liters per minute. So we are going to find the QT or the quantity in kilograms of sugar at time t and find the amount of sugar in the tank when the tank fills to capacity or at which the process stops. For the solution, just like last time, we have dq over dt, which is equal to the rate in minus rate out. So we have here dq over dt is equal to the product of 1.5 kilograms over 1 liter times 5 liters over 1 minute minus the product of qt in kilograms over 2000 plus 2t in liters times 3 liters over 1 minute. Observe that since the net difference of mixture in is 2 liters per minute more than the mixture out, the volume in the tank is increasing by 2 liters per minute. So the expression 2000 plus 2t gives the total volume of solution in the tank after t minutes. There are 13,000 liters available in the tank, and if the tank fills at 2 liters per minute, then the process will run for 13,000 divided by 2, which is equal to 6,500 minutes. Thus, the bounds on t are t is greater than or equal to 0 but less than or equal to 6,500. And the initial condition is q of 0 is equal to 50. Now, simplifying the differential equation, we have here q prime is equal to 7.5 minus 3 over 2000 plus 2t times q. So we already know that the t is greater than or equal to 0 but less than or equal to 6,500, and our Q of 0 is equal to 50. So we have to write the differential equation as Q prime plus 3 over 2000 plus 2t times Q, which is equal to 7.5. The integration factor is e raised to the integral of 3 over 2000 plus 2t dt, which is equal to e raised to 3 halves ln of 2000 plus 2t, which is equal to e raised to ln of 2000 plus 2t raised to 1.5, which is equal to 2000 plus 2t raised to 1.5. So the solution is Q of t is equal to the integral of 7.5 times 2000 plus 2t raised to 1.5 dt plus c all over 2000 plus 2t raised to 1.5. So simplifying, we have here 3 halves of 2000 plus 2t raised to 2.5 plus c all over 2000 plus 2t raised to 1.5. So the general solution is Q of t is equal to 3000 plus 3t plus c times 2000 plus 2t raised to negative 1.5. Since we already have the general solution, which is Q of t is equal to 3000 plus 3t plus c times 2000 plus 2t raised to negative 1.5, and we already know that the initial condition is Q of 0 is equal to 50, so we have to solve for the value of c. So to find that, we have here 50 is equal to 3000 plus 3 times 0 plus c times 2000 plus 2 times 0 raised to negative 1.5. So simplifying, we have here 50 is equal to 3000 plus c times 2000 raised to negative 1.5. To get the value of c, we have here negative 2950 is equal to c times 2000 raised to negative 1.5. So we have here the value of c, which is equal to negative 2950 times 2000 raised to 1.5. So there is no reason for us to actually calculate the value of c. Thus, the particular solution is Q of t is equal to 3000 plus 3t minus 2950 times 2000 raised to 1.5 times 2000 plus 2t raised to negative 1.5. Now, from the last slide, the particular solution is Q of t is equal to 3000 plus 3t minus 2950 times 2000 raised to 1.5 times 2000 plus 2t raised to negative 1.5. So the flow runs for t, which is equal to 6,500 minutes, at which time the vat is filled. At this time, there is, or we have to substitute the value of t to 6,500. So we have here Q of 6,500 is equal to 3,000 plus 3 times 6,500 minus 2,950 times 2000 raised to 1.5 times 2000 plus 2 times 6,500 raised to negative 1.5. So simplifying, we have here Q of 6,500 is equal to 3,000 plus 19,500 minus 2,950 times 2,000 raised to 1.5 times 15,000 raised to negative 1.5. So Q of 6,500 is approximately 22,356.4 kilograms of sugar. So, is this plausible? Suppose the process run forever, in which we have equal amounts coming in and leaving. A 15,000 liter vat of solution would have 1.5 kilograms of sugar per liter, or a maximum of 15,000 times 1.5, which is equal to 22,500 kilograms of sugar. We expect our figure to be little below that maximum, so an answer of 22,356.4 kilograms of sugar is very plausible.